Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to continue our conversation about acids and bases, but now we're going to focus much more intensely on how a proton can move back and forth in between an acid and a base. So a good place to start is looking at our weak acid-base behavior that we talked about last time. So if I'm reacting acetic acid with a strong base, like hydroxide, what we end up finding is that the proton moves from one group to another. And this ends up producing an anion behind and water. And what we're really doing is looking at a proton shuffle. And this was originally collated as a definition by Bronsted and Lowry, who defined an acid as a proton donor. And if we take a look at most of our acids, for example, our strong acids like HCl, they lose a proton to form chloride. Our weaker acids like acetic acid loses a proton to make acetate. And this also holds for a whole range of other compounds like phosphoric acid, which can lose multiple protons. In contrast, we have something, when we're looking at our bases, they need to be able to accept a proton. So our classic strong base, according to Arrhenius definition, involves hydroxide. And the reason why is because if hydroxide is present in solution, it can readily pick up a proton to make water, and water is very stable. We also have plenty of bases like amines, not just free amine, but also organic amines, which can protonate to form a positively charged ammonia-based species, which are still quite stable in water. And one of the reasons why your body makes such heavy use of amines, because it's often useful to have a base around. But it's also worth noting that if I have an acid that can donate a proton, this also leads to a product that can accept a proton. So every acid, when it loses a proton, can make a base that can take that proton back, which again makes sense when we're looking at weak acids and weak bases, because they don't perfectly go one direction or another. They go back and forth in between the two species. So any weak acid will form a weak base. But one of the important things to remember when we're looking at this Bronsted acid-base behavior is because what I'm looking at is a proton moving back and forth. It means that acids and bases can't exist on their own. They have to exist alongside each other because it takes two to tango. To have a proton donor, I have to have a proton acceptor. Now, one of the other cool things that ends up happening when we're looking at this acid-base behavior is you may notice that we're generating a lot of charged species, whether it's, say, a chloride or an ammonium. And as a result, whenever we're trying to react an acid with a base, we almost always end up producing some sort of salt product because we have free ions, and ions interacting with each other is a salt. However, the identity of that salt product can be quite varied depending on what I'm reacting. So let's go ahead and say I'm taking something like HCl and amine, two neutral species. I go ahead and react them together, and I produce ammonium, positively charged, and chloride, negatively charged. This makes ammonium chloride, which is actually a fairly abundant salt. This actually doesn't have to happen with free amines, but it can happen with organic amines like methylamine. It combines with HCl and it makes methyl ammonium chloride. Again, whatever is hanging off that nitrogen can be quite flexible. The big thing is that it accepts a proton, gets a positive charge, which means it has to have an anion to hang out with. However, it's also possible to take things like our deprotonated acids, which again form our weak bases. But in this case, I have to start with the salt. Mostly I'm looking at something like sodium acetate, which we've looked at previously. It can go ahead and react with HCl to make acetic acid. However, we are left behind with that free sodium, which dissociates, and can then react with that chloride to make our good old friend sodium chloride. And this can hold for any number of other weak acids or bases, like sodium nitrite with hydrobromic acid, weak base with a strong acid, making a weak acid nitric acid, and a salt, sodium bromide. So we can produce quite an array of species. However, one of the things that is worth noting is that not all acids can donate a single proton. Some can donate multiple protons. And this includes rather famous species like phosphoric acid. It can go ahead and react with sodium hydroxide to make a monodeprotonated salt, which can then react with more sodium hydroxide in solution to lose a second proton and even a third. So in this case, phosphoric acid has 3 acidic protons, all of which are fairly easy to remove. And so whenever you're looking at phosphates in solution, they're almost always complicated by the fact that you may have multiple of these acids or bases present at once. And in fact, there's many common polyprotic acids that you deal with regularly. This includes things like sulfuric acid, carbonic acid, which is often used to acidify sodas and produces CO2. We also have things like oxalate, which can react and bind metals, and hydrogen sulfide, which is infamously part of the stinky part of farts and rotten eggs. That's that sulfur smell. However, it's also possible to form polyprotic bases, which can remove at least multiple hydroxides, or if you think about it in terms of a Bronsted definition, accept multiple protons. So if you're looking at that Arrhenius definition, you have something like calcium hydroxide. It disassociates to form 2 hydroxide groups. However, if you remember back to solubility, this isn't perfectly soluble. So in order to really donate those hydroxides, they have to have an acid to react with to turn those hydroxides into waters. However, you also have things like ethylene diamine, which is a common way to, again, bind metals, as you'll find with a lot of these bases. It can react with HCl twice in order to accept 2 protons and make a quite complicated salt. However, one of the things that is important to remember is that if I'm trying to react a weak acid with a weak base, the reaction doesn't always go to completion. So for example, I can take something like acetic acid with sodium fluoride. So fluoride makes a weak base. It will react to form a weak base, sodium acetate, and hydrofluoric acid, which is a weak acid. However, because I have a weak acid and a weak base as a product, it means it can also go in the reverse direction. So this is a common complicating factor whenever I have a weak acid and a weak base, is the reaction goes back and forth and can really be best described as an equilibrium reaction. And all 4 of these species will be present at once. And we're going to be looking a lot more at these kind of complicated equilibrium systems next semester, as they form a lot of very relevant chemistry. But the important thing to remember now is that whenever you have these weak acid, weak basis systems, you're going to have multiple species present all at once, because reaction doesn't go to completion and you'll never have a perfect yield. However, one of the things that is worth noting is that if I was going to try and do this with even a single strong acid or strong base, it won't form equilibrium. Instead, it will go to completion. And one of the reasons why is any free protons will completely react with your weak base, like your sodium fluoride, to make an equal amount of hydrofluoric acid. And similarly, any free hydroxide will completely react with your weak acid to form the conjugate base. And so this is an important thing to keep in mind with acids and bases mixing together. However, we won't spend too much time on weak acid, weak base reactions, but it's important to know that they exist. So next time, we're going to dive a little bit more in detail with acid-base behavior as we look at titrations. And one of the ways we can use these reactions to help determine the concentration of relevant species. Until then, take care.